previous amplitude modulation is that the message is no longer go to the amplitude, right? It goes into the angle. So what is angle is that here, this is a carrier, and we see that here, this parameter, that's called as angle. So our message goes to the angle, and when you look at the angle, here, we have a frequency portion here, and we also have a phase. So when you put the message into the phase, like what you see here, then we call that as a phase modulation. And when you put the message into the frequency, so your message is a part of the frequency, like this, right? Your message is still a function of frequency. This is a carrier frequency, FC, plus the message. So message becomes a part of your frequency. Now you get a new frequency, FI, right? So in this case, we call that as a frequency modulation because your message goes into the frequency. Now, because of your message, your frequency eventually changes, okay, because of the message. So that's your frequency modulation. So when you look at here, since your message goes into the frequency, when you put this one into the angle, now in this angle, what you see is that eventually it's going to be like 2 pi f ct plus some other phase, the integration of the message, right? So when you compare the phase here, angle here in the phase modulation, and also compare that with the angle in the frequency modulation, the difference between PM and FM is that in the PM, your message is in here as a phase, but in the frequency modulation, your message is first integrated, okay, and then go into the phase portion. But this is a frequency modulation, right? So remember that how the message goes into the phase in FM, because your message is part of the frequency, but still it looks like a phase, right? It's an integration phase. Remember that how we look at this way? So remember that eventually the message goes into the frequency when you put this frequency into here, right? Then since the frequency has 2 different terms, you split into 2 different terms, then eventually the second term you will see the MP times T, right? Remember that, remember all the mathematics we had before? Then eventually MP times T is almost the same as your integration of M tau, because it's the area under the M tau, right? So that's an easy kind of connection between this equation and that equation. So that's something that you want to remember. So eventually the transmitted signal, ST, in PM looks like this. It's pretty simple to understand, right? And FM, whereas FM looks like this. So that's your eventual message that you are transmitting. Okay, so this is a summary of a PM and FM. So here's a PM column, and we have a FM here. So PM, we have an angle like this, and FM, instead, we have like this form. Okay, so just remember this one goes to the message. I mean, PM, in PM, the message goes to PM, the phase. This one goes into the frequency originally, but when you expand it, then it becomes like this. So this is an example. Let me just skip this one because I believe that you understand all these things. Let me just briefly skip those things and also skip this one. This is one example, right? And your message is 0. That means you're going to get just a carrier frequency. This is a carrier frequency. But when your message goes into linear, like this way, linear curve, now then your message is a linear curve. So put this linear curve message into the phase, because in the phase modulation, your message goes into phase, right? Put this linear input into the phase. Now then your output, this is ST, right? You are transmitting this one over the air. When you put this one as a message into the PM, into phase, now this is the transmit signal from the phase modulation. And how you understand here is eventually phase, this is a time domain. Phase is changing on its pace, right? It's changing on its pace. But since you are increasing in the message, actually increasing in positive way, your phase is moving a little bit faster. So that's why it's like you are moving a little bit faster, right? From here, the phase 0, here is a 90 degree, here's a 180 degree. So from here, phase 0 to the phase 180 degree, you have this much of space, but in this case, you have a short, which means that this one, the phase is changing a little bit faster. This one, phase is changing this speed, but this one is changing faster. Why is it going faster? Because you're increasing, right? Your message is increasing. So that's a little bit easier to understand. Because when you look at this figure, this output, it looks like it's a FM, right? Because when you look at here, it looks like a frequency has been changed. That's how it looks, right? But in fact, that's not the case. This is a PM. Phase is changed, not the frequency. But it looks like a frequency is changed. Why? Because your phase is moving a little bit faster now, because your message is increasing positively. So that's why we get this kind of figure as output from the PM. And this is output from FM. Okay? Now think about it. This is a message. And remember the FM, what you need to do is you need to do integration. And this is like AT, right? And you are doing integration, it becomes half of the AT square. And put this half of the AT square into the phase term. Now then, this is a square. Your phase is even more faster. Is even faster, right? Square. So that's why it's becoming much, much faster this way. Okay. So this is just difference between PM and FM. So your message is coming, first integration, doing phase modulation, then you're going to get FM. So this is another way. What we're going to talk about today is FM. Okay? So we are mainly talk about frequency modulation today. And first of all, we're going to talk about narrowband frequency modulation. So what is a narrowband? Narrowband means your frequency bandwidth is narrow. It's like a small bandwidth. That's what they mean as a narrowband. Okay, so let's take a look at it. We have a lot of equations here, but that's not that difficult. Okay, so let me explain one by one. As an example, let's start with our own example. We always start with this kind of example, right? Our message is a simple sinusoidal function. Okay, this is our message, MT. So our MT is simply a cosine. If our message is simply cosine, we have done this many times before. Before when we discussed amplitude modulation, at that time we also used this example. We always use this example as a message, right? Simple message. Okay, let me go back and review the AM. So we talked about the DC added amplitude modulation first, and we also talked about DSB and also SSB, right? That's what we discussed earlier. And let's say our message is this, the cosine. AC cosine 2 pi FMT. And FC, let's say, is a carrier frequency. Eventually, using this message, and let's say you are doing the AM, the DC addition, DC added AM, then what is the output? Let's draw in frequency domain. So here's a frequency domain, and here's the FC. Let's draw only the positive frequency. So what is the picture eventually for ST? So it's a frequency domain, so let's draw SF. SF is the frequency response of your ST, okay? Modulated signal. So what does it look like in this case? It's going to look like this cosine will have this kind of impulse in your original message, right? And also you have carrier component. Remember that? This is going to be your output in the frequency domain. So that's what you're going to transmit over the air, but this is just a frequency plot. So that's what you see in this case. Now what happened at the DSB? Using the same message, you do the DSB modulation. What do you get? You're going to get this kind of frequency response, right? That's your SF when you do the DSB, right? In DSP, you don't have a carrier, right? You only have both sides, your sidebands. That was your modulated output. What about in single sideband? In single sideband, depending on upper single sideband or lower single sideband, let's say in upper sideband, you're going to have this one, right? Just one. That was your output. So now, using this as a message, I'm just giving you an example of this message, right? This is the example of our message. When we use this message, eventually you're going to create this frequency response, or this one, when you transmit. Okay, this is SF. You know what SF is, right? This is the frequency response of ST. ST is what we are transmitting over there. Okay, so that is your frequency response of the signal you are transmitting over there. Okay, so that was a case of AM, amplitude modulation. Okay, that was the case. Now in our FM, we're going to start pretty much similar way. So let's say our message is same message, same thing. That's our message, right? And put this message into the frequency, because what we are going to do is a frequency modulation. So let's put this message into a part of the frequency. Okay, let's do it that way. So here's our carrier frequency FC plus our message here. But when you put this our message here, we are going to multiply our coefficient, some gain, and let's call this a KF. Okay, KF. Just a gain, just a constant value. Okay, just constant value KF times MT, and that's our frequency. And what we're going to do is we're going to group these two, KF times AM. Both are just simple constant value. Group this and change this into delta F. So eventually then the FIT, which is the frequency after you do a modulation, that frequency becomes FC. What was the FC? That's your carrier frequency plus delta F cosine 2 pi FMT. So when you look at this, now what do you get? What can you see is that this is the frequency after you do modulation. We are talking about FM modulation, right? So the frequency will be changed. Okay? Yes. After you do modulation, now the frequency is changed. So that's your output frequency. And how things are changed is that your FC is a carrier frequency. So that's the reference frequency. Here's the FC. And here, let's look at cosine. What is the maximum value of cosine? 1. So if this is a maximum, then it becomes 1. Then what is the maximum frequency you have? FC plus delta F. What is the minimum then? FC minus delta F. So that's the range. So here's FC. Now it can go to the FC plus delta F or FC minus delta F. Okay, that's the range of the frequency variation. Okay, that's your output frequency. So since this is FM, your frequency is changed, but your range of frequency change is from FC minus delta F to the FC plus delta F. That's the range of frequency variation. Frequency changes between that range. Okay, that's what they mean. Okay, we call that as a frequency deviation. Okay, this one, delta F. We call this delta F as a frequency deviation. Why do we call it this way? What is the deviation? How far this is from your reference? That's deviation. So or FC is your carrier frequency, original carrier frequency. But when you transmit, actual frequency is deviated from the FC by this much. So this is your actual frequency that you are using to transmit signal. This is a carrier frequency, but that's a delta F or some other deviation. So that's why we call this one as a frequency deviation. Okay, and your frequency changes between that region. Okay. Now put this one message into here, because that's the angle. What we discussed here is a frequency change. So that's a frequency, but this is the angle. So based on this FM equation, let's put this, our message, into here and do an integration in order to get the angle. Now you are going to get this one, because let's do the integration. Okay, let's do integration. When you do integration, this is a constant anyway. So integration of cosine becomes sine, right? Becomes sine, just plus sine. And then when you do the integration with respect to t, now 2 pi fm goes onto the front like this, right? So, and 2 phi cancels out with this. With 2 pi fm goes down here, and 2 phi, and this 2 pi cancel out. So eventually you're going to get this. When you do the integration of mt, you're going to get this. So this is the angle, 2 pi fct plus delta f divided by fm sine. So that's your angle when you do the fm. Okay? And what we're going to do is we're going to put this delta f divided by fm, and we're going to replace that as a beta. And beta is, we call this a modulation index. Remember that we had a modulation index in AM. Remember that? What was the modulation index in AM? In AM, let me remind you one thing. In AM, in here, in this area, DC edition, we had a modulation index at that time. And when you change the modulation index, right, sometimes you are going to you want to have a very big carrier and small energy here. Or if you change the modulation index value, sometimes this carrier energy is smaller and this energy in sideband becomes bigger. Do you remember that? So that's the modulation index. You can basically change the value of modulation index in order to balance the energy between these two. So that was a modulation index at that time. Now in FM, we also have a modulation index. And this modulation index here, we can simply call this one as a beta, and this beta is a modulation index. Okay? So that's this here. Beta equal to delta f divided by f. That's the modulation index. But when you look at here, right, this is the angle. Okay, angle. So 2 pi fct plus something. And this something here is a phase, right? Because this is an angle. Angle is like a 2 pi fct plus phase. This is a phase term. And inside the phase term, you have a beta times a sine. And sine also has a maximum value 1 and minimum value -1. So this beta, you can also call that as a phase deviation. So simply speaking, this is a frequency deviation. Okay? How much frequency is deviated from the FC? That's the frequency deviation. Your frequency is deviated from the FC. So how much deviated? That's this much. This beta is a phase deviation. How much phase is deviated? That's a phase deviation. But when you compare this frequency deviation with the phase deviation, now you can see that phase is a delta f divided by fm. Okay, that's the phase deviation. Okay. So given that, let's go to the next slide. Now we just got an angle. The angle we just looked at in the previous slide was 2 pi fct plus beta sine. That was the angle we just looked at. Okay. So let's put this angle into the original ST. Okay, let's go back to the previous slide. So what we discussed here is that we got this angle, and the angle looks like this. But this angle theta IT eventually should go to, let me go all the way. Eventually should go to here, right? That's the angle. So we want to put that angle into here in order to get the ST. ST is what we transmit over the air, right? So we just discussed this angle. So let's go all the way to here. That's this one. So this one is the angle. So let's put this angle into the carrier like this. Then now we get the transmitted signal ST. Okay, so this is what we transmit. Now when you look at here, what you can see now is the cosine alpha plus cosine some a plus b. Something like that, right? Cosine a plus b. So using the trigonometric identity, cosine a plus b equals the cosine a cosine b minus sine a sine b. Okay, that's another identity. So simply from here to the second line, just use identity. And we just split this one into 2 multiplication of cosine minus multiplication of sine. Okay, simply that's the way. So far it's just a mathematical manipulation, right? I didn't do anything, just using the identity to change it from here to there. From here, now we're going to use a little bit of trick. The trick here is, since this is a narrow band, what that means is your bandwidth is narrow. What that means is this beta, modulation index beta, we can call that as a small. Okay, we call that as a beta is a small. And then if the beta is a small, what we can assume is that, let's say cosine beta. And if the beta is small, very small, like a 0.001, something like that, then we can always assume this one equals to 1, right? Cosine some small value becomes 1. We can simply approximate. Similarly, sine beta, and beta is very small. In this case, we typically assume that this one is the same as beta. Okay, typically. So why we do that is cosine looks like this. So when you have a beta small, then it's almost like 1. But when you look at the sine, when beta is small, then it looks like a linear curve, just approximation. So that's why sine beta, when beta is small, we typically approximate sine beta is almost equal to the beta. Okay, that's a very common assumption, very common approximation. So using these two approximation here, same way, now if we assume that beta is small, very small, then this one cosine beta times something, this whole thing, the cosine, now we can assume that this is approximated to 1 because beta is small anyway. So cosine beta, let's say this is 1. Here we have a sine beta, and as I said here, sine beta is typically approximated as a beta. So this one is a sine, beta sine. So when you approximate these things, we're going to put these things out. So just remove sine and put these things out. Okay? So cosine here approximated to 1, then this one becomes this, simply. And when you put sine, beta sine, we approximate this way, then we are going to get this. Because AC sine 2 pi fct still here, AC sine 2 pi fct. And the later one, this whole thing, this sine and beta sine, this whole thing is approximated as beta sine. So beta sine, we bring it out. So beta goes out, goes to the front, and sine is here. Okay. So this second line is simply approximated into that line. So now you can see the approximation here, right? This one. Not exact, but very common assumption. So that's what we get. This is only true for narrowband FM. Why? Because we assume that beta is small. Only the beta is small, we can approximate from this to this. Once we go to here, once we have this equation, now what we are trying to do is, here you see that sine times sine, like a sine A times sine B. Okay? Sine A times E. So by the way, here, these are approximation. Cosine beta something, that's approximated to 1. And sine something is approximated whatever inside you get here. Okay? That's the approximation I used from here to there. Okay? That's what we do. So using these two approximation, we get this one. Now from here, we see that it's a sine A times sine B. So when you have a multiplication of two sine, again, we are going to use the identity and to change it to some other equation, like this way, or like this way. Okay? So we have after approximation, we get this one, and sine times sine, sine A plus sine A times sine B. Now sine times sine can be changed into cosine. It's like sine A times sine B. It's cosine A plus B minus cosine A minus B. Okay? So that's how you change it. That's another identity. And once you use that identity, now from here to here, simply use the identity. Okay? That's it. You know, I didn't change anything, just use the identity. Now once you do this, that's the final equation for narrowband FM. That's the final equation. But what we are trying to talk about here is this is a final signal, transmitted ST signal for narrowband FM. But I want to compare this one with the original traditional amplitude modulation output. So look at here. This is an equation that you already have for AM. This AM, this. Let's look at this equation. This one was the output from the original DC added amplitude modulation, right? Let's write this one. Let's write this one in equation. When you write this equation, this one, the middle one is the carrier, right? So what is this one? AC times cosine FCT. Because this is a carrier, we know that this one is AC cosine 2 pi FCT. Okay? Plus the side bands, we probably have a half and cosine 2 pi FC plus FM T plus cosine 2 pi FC minus FMT. This is same as this one. Right? So that was the output when we have the DC added amplitude modulation. I'm talking about amplitude modulation, right? We learned that like several weeks ago. So when you have a DC added amplitude modulation, we got this one as a spectrum for the transmitted signal. And when you write this one in equation, this is the equation. This is this one. I'm talking about this equation. This was the equation you already have in the DC added amplitude modulation. This one. This one is this equation. Okay, we already have this several weeks ago. And now in narrowband FM, we eventually come to here. And what I'd like to do is compare the narrowband FM signal with our previous DC added amplitude modulation. It looks like very similar, right? Actually, it's almost the same. The only difference is that in the previous amplitude modulation, we have a plus. Now in narrowband, we have a minus. That's the only difference. It's the same. Otherwise, it's the same. Okay, exactly same. The only difference is that this one is a minus. That's the only difference. So what that basically means is that when you have a very narrow band FM, we are talking about FM, right? But the assumption here is this is a narrow band. When you have a narrow band FM, the output signal is almost the same as your amplitude modulation, as you can see here, right? Only the sign is different. Looks like almost the same. Okay, that's the message, simply. But since we have a minus here, and the original amplitude modulation, we have a plus, let's draw these things in phasor notation. So this is the figure. You say the phasor interpretation. So what that means is that this one shows the two different figures, right? The upper one is the case of narrowband FM. The second one is the original amplitude modulation. So in this amplitude modulation here, what we see is the big arrow here, that's the carrier. So we have three terms, right? We have a first term carrier, second term upper sideband, lower sideband, right? We also have a three arrow. The middle one is a carrier, upper sideband, lower sideband, right? We have a three impulse. So we have three of them. Same thing here. The big arrow is the carrier. This one, upper sideband. This one. This one is a lower sideband. Okay? So this upper sideband and lower sideband, we make a vector like this. And the output is going to be the addition of these two vectors. So the output goes to this way. And this output, upper sideband and lower sideband, make this another vector here. That vector is aligned with the carrier. So that's the amplitude modulation case. But in the narrowband FM, what we have is we still have a same carrier. So this carrier, the big arrow, is the same. So big arrow here as a carrier. And we also have an upper sideband. Same thing. Same direction. Same size, right? Same. But we have in this AM, we have a lower sideband go this way, but this one is the other way because this is a minus sign. So it goes the other direction, right? In this amplitude modulation, it was going that way. That's what happened here, right? But in the FM, we go that way. So therefore, when you add this vector, that vector, the output added vector goes up. Okay? So since this is the output of this vector plus that vector, now eventually your carrier will be also added with that. And now the resultant means the final output now goes to that way. So that's only difference. But this is just to help you to understand what this means. Okay? What this means. And the difference between the narrowband FM and this amplitude modulation, just to show the difference in the phasor interpretation. Okay? And the previous slide, this one shows you the block diagram, how you can make this block. Okay? This is a message, your message going into the integrator because this is a FM. And once you do that, now you are multiplying, your message is multiplied by a sine carrier. And that is subtracted from your cosine carrier. That's what happened here, right? That's what happened. So you have a message. Your message was beta and sine. That was your beta cosine. That was your original message. But that was here. Original message was like a cosine, right? Cosine 2 pi FMT. That was the original message. Now you are doing integration. Your cosine message becomes a sine. Now that sine of your message is multiplied with the sine carrier, like this. So once you multiply that, right here, you're going to get this term, second term. And you put the minus, so you have minus. And also you are adding the cosine carrier. So that's what you do, cosine carrier, add it. So eventually you're going to get narrowband FM. So this block diagram is just simple. It's just the same as this mathematic equation. So you can just draw this way, this mathematics, both are same, exactly same. Okay, so that was the narrowband modulation, narrowband FM modulation. So the important message in here is when you do this narrowband FM modulation, your output, this is what you transmit over the air. Okay, so this output looks almost the same as previous amplitude modulation, almost the same. Okay, only difference is minus. That's the message. But now the thing is, this narrowband FM is not really used. Okay, we don't use it much. Okay, this is not good. I mean, we don't use it that much. So what we typically use, when you look at the FM radio, right? FM radio, that's not this one. what we typically use in FM radio is this wideband. Okay? This wideband. When you have a wideband, now the beta is not that small. Okay, in the previous FM, the narrowband FM, let's go back a little bit here. In narrowband FM, the big assumption we have was beta is small, so therefore we use this approximation, right? Cosine becomes 1, sine becomes just this one, right? That was the assumption we had, big assumption. But when you consider the wideband, we cannot have this assumption. We cannot have this, right? So now things are complicated, very complex. Because this assumption makes things very easy, right? When you use this assumption, this one now becomes simple, like this. It's much simple, so things are easy. But now think about the wideband. We cannot use this assumption, then things are very complex. That's what we're going to talk about here in wideband. Okay? Things are going to be very complex. So to do that, we need to go back to original equation. So original equation is this one. I'm going to go back all the way to this one, right? This is our original FM. We started from here, and we just use the identity. We rewrite this one into here, and using this approximation, we make it simple, right? But in wideband FM, we cannot make it simple. So we have to all the way, we have to go back and restart everything from here, right? So that is our starting point. So that's our starting point, okay, going all the way back. And this one was the example that our message was this one, okay? Still, we are using this one as our message. Our message is a cosine. So therefore, when you do the FM, first thing is we are going to do the integration, right? We first need to do the integration like this. So when you do integration of this cosine into here and do integration, now you're going to get sine, right? Okay, so this one is our original FM signal when you use this cosine as your message. Okay? You understand the link between these two, right? Do you understand that? Yeah, so put this message into here. Now you're going to get the sine. Okay, so this is our original FM signal. Let's go to wideband. So here's a starting point. In order to start in wideband, what we want to do is, here's a cosine. And in the cosine, what we can write is let me this way. You know the cosine x. Cosine x. We can also write it as this way, right? So what is the exponential jx? Let's say exponential jx. What is this one? It's a cosine x plus j sine x. Okay? But when you put the real, if we take the real of jx, what is that? It's just cosine. Because this is a real component, right? I'm just bringing the real component. So this one is the same as a cosine. So real component of exponential jx is simply cosine. So same way, what we are seeing here is eventually cosine. It's inside the cosine we have some complex thing, but still this is just cosine. So what we're going to do is that we're going to take a real component of AC exponential of j of all these things. Okay, we can rewrite it this way. That's what you see here. That's what you see here. Okay. So this one, it looks like a different, right? Because real component of exponential something something, it looks different, but it is actually same as our previous cosine. It's the same thing. Now in here, in order to make it simple, what we want to do is, first of all, this one is a exponential of a plus b, right? So like exponential a plus b is same as exponential a times exponential b. Same thing, right? So therefore, what we want to do is we want to change it into ac times this exponential. We have two terms. So exponential of the second term, we're going to bring it into here, j beta and then put this one here. Like that. Okay. Simply, we split these two into two different exponential and bring the second exponential here, and this one goes there. The reason that we want to do is this is a carrier component. You see that there's a frequency, carrier frequency, right? So this is a carrier component. What about this one? This is not carrier component, right? What is this one? This one is your message. Look at the frequency. This one is FM. The frequency is your message frequency, FM. So this is not the carrier component. This is your message. So bring the message, simply as separating message with the carrier. And since this one is a kind of message, still is a part of the message, I'm going to put it as a S tilde tau, a tilde t, like this. That's why you get this one. S tilde t is still like a message, but it's not exactly same message, but some message. So it's S tilde t. And the exponential j2 pi fct, this is a carrier component. So we're going to separate that like this. Okay. So this is a selection of your S hat t, S tilde t, like that. Now things look a little bit simple now because we separate it by, here's a carrier component. This is your message component. Right? Now the carrier component, we don't care because the carrier looks like this anyway. So we don't do anything about carrier. What we are interested in now is this message component, S tilde t. This is what we are interested in now, okay? And when you look at this one actually looks a little bit complicated because this one looks AC times exponential j beta sine 2 pi fmt. That's our S tilde t, right? Have you seen this kind of equation? This equation is like exponential, and here in the exponential exponent you have a sign, right? So exponential of j beta sine something. You haven't seen this equation before, right? This looks a little bit complex. You know, any equation, that kind of equation, we can use Fourier series. So what we are trying to do here is that we want to expand this S hat t there. We want to expand this in the form of Fourier series. Okay? So original S hat t is that one. That is original S hat t. But we're going to rewrite it. We're going to expand it into the Fourier series like this. And the Fourier series is like a sigma of n from minus infinite to positive infinite. And we have a Fourier coefficient, Cn, times exponential terms. And here inside exponential terms, now what you can notice is this one has a FMT. Why? Because we have FM up here. So that goes in here, FM. And we also have N here, N. Here you have N. So we can expand this into that way. So that equation is the same as this equation by Fourier series. So once you do that, now we want to calculate these kind of complex integral equation, but we don't care, okay? You don't have to worry about these things. We're going to never do it. Okay, so doing all these things, eventually, let me give you only conclusion. Eventually, all these things we're going to get is our Fourier coefficient Cn is simply Bessel function. You know, have you heard the Bessel function? Yeah, so this is a Bessel function. This is a Bessel function with nth order and the first kind nth order. So Bessel function is defined this way. This is the original definition of a Bessel function. Okay, but we don't care at this point. What we worry about is Cn is a Bessel function. And what was the Cn? Going back to slide, Cn is this one. When you do the Fourier series, Cn is a Fourier coefficient. And why do you need the Fourier coefficient? Because we want to represent this SAT a little bit simple way. So this one looks complex, right? That's why we're gonna expand this into this way, and the coefficient here is the Fourier series. Okay? I know that this is not easy, but let me explain the next slide. Then it's probably a little bit easier to understand. So eventually you get this one. The Cn, the Fourier series coefficient, is going to be the Bessel function. So let me go to the next one. So your SAT, okay, is a summation of a Bessel function. It's an addition, summation of Bessel function. But when you look at here, what you can see is that this one is simply a Bessel function. So eventually the Bessel function is a coefficient. When you have a different n or different beta, you're going to get the different value. But still, that's going to be constant. Let's say if the n equal to 1 and beta equal to 2, then put this n equal to 1 and beta equal to 2, then this Bessel function gives you only one value. So eventually, this value is constant anyway. Okay? So when you change the n or change the beta, Bessel function gives you another value, but still that's constant. So you don't have to worry about this Bessel function. And you are not going to calculate it. Then who's going to calculate it? Computer will do it for you. Okay? You're going to use a computer to calculate this value. So you don't worry about it. Now using this one as the coefficient, what is important is the second term. When you look at the second term, now what you can see is exponential of j2 pi n fmt. So what does that mean? And n is in the summation. It changes from minus infinite to infinite. So here n is changing from minus infinite to infinite. So what does that mean? Now that you have infinite number of frequency component. That's the important thing. That's the important thing, okay? So I'm going to talk about that in the next slide. So that's what it is. Eventually, we just talked about S hat t. And where was S hat t? Original S hat t was from the ST. So going back to the previous equation, we're going to put this S hat t into the original place here. Then you're going to get ST. Okay, that's our original ST. So eventually, when you do the wideband FM, this is the signal we are transmitting over there. Eventually, this is what we are transmitting. Simply, okay? That's the conclusion. So this is our signal that you transmit over there. This one looks very different from amplitude modulation or narrowband FM or any of the signal we just discussed so far. So this one looks very different, right? Why this is very different? First thing, you have infinite summation. And second thing, you have so many different frequency components, right? Look at here, this is a frequency. You have FC plus NFM, but N changes from minus infinite to infinite. So it's like
FM, FC plus, if n equal to 0, that means just FC. If n equal to 1, FC plus FM. If n equal to minus 1, FC minus FM. Something like this, right? N equal to 2, then FC plus 2, 2FM. So we have infinite number of frequency components. That's what they mean in this signal. So that's very weird because our original signal, okay, so simply let me draw the previous picture again. So if you do AM, our previous DC added AM or DSP or SSB, in the frequency domain, we get these things or these things or this, right? We get these things in frequency domain. Now, because our original message here, original message looks like this. This is our original message, right? Now you do the DC added modulation, you're going to get this. You're going to create this one. Also DSP here and SSB, you're going to create this one. But when you do the FM, wideband FM, what is going to be the frequency? As you can see here, this is a summation. And there are so many different components. So this one was our original message. But eventually, your output, after you do the modulation, FM modulation, your output is going to be like something like this. You have so many different frequency components. This is like FC. This one, FC plus FM, FC plus 2FM, FC plus 3FM. Okay? There are so many of them. Then what is the length, what is the height, what is the amplitude for each of them? Some of them is big, some of them is small, right? What is this size of that? That's there. That's the Bessel function. So Bessel function gives you how big each impulse function is. Okay, how big it is for each of them. But it's basically infinite number of frequency. Okay, that's very different from our previous amplitude modulation. So let's look at that in the picture here. First of all, we want to look at the Bessel function. This is the Bessel function. Okay, it looks like a complex, but that's not actually. So let's look at here. If the n, here the subscript here is n. If the n equal to 0, then this is the function. Okay? If the n equal to 1, then this is the Bessel function. Now here inside the beta, that's your x-axis. That's a beta. So let's take an example. If let's say the beta, what is the beta, by the way? Our modulation index. Okay, we discussed modulation index in FM, right? That's the modulation index. So this one typically is a constant. Let's say our modulation index is 1, as an example. Okay, if the modulation beta is 1, then we are talking about here. So if the beta is 1, then what is the value when n equal to 0? Here. Okay, what is the n equal to 1? Then here. If the n equal to 2, then somewhere here. Okay, that's the output. Okay, so that's going to be your output. So let me just move to the next slide. So that's what you can see as an example. Let's say the beta, modulation index beta, let's say it's the 1. And this one shows you the case of beta equal to 2. This is the case of beta equal to 5. Okay, so we basically compare the different modulation index. And when the beta equal to 1, now you see several impulse functions here, right? And when the beta equal change, now you see the different, and this is different. In fact, here we also see the infinite number, but this area is so small, so you don't see it, but there is infinite number. So this is going to be the spectrum when you see the FM. generally it doesn't make sense, right? How can you use infinite number of frequency? In that case, you are using the whole frequency. You cannot do it, right? Always a spectrum is given to you. You can only use some limited bandwidth. Okay? So you cannot use the whole bandwidth. So therefore, what we need to do is mathematically FM has the infinite number of frequencies, but what we need to do is we have to cut. We have to use only some bandwidth, and the rest of them we have to remove it. Does it make sense? We have to cut it. So that's what we need to discuss. Yeah, I think we can discuss it next time.